Let's compare the following compounds. Which one is more acidic? We begin by removing the 2 protons here to get the corresponding conjugate bases. As you can see here, we recognize the pattern, a lone pair or negative charge next to a double bond. So we can draw the corresponding resonance structures. To answer this question here, the 2 factors that we saw previously are not sufficient, because in both cases, the negative charge is on oxygen, and the negative charge is equally shared between 2 oxygen atoms. So there must be a third factor. And if you examine carefully the 2 structures, you will see that there is a difference here related to the presence of chlorine atoms. So what difference does that make? For this, we need to understand a concept called induction. We know that electronegativity measures the affinity of an atom for electrons. So what happens when you have 2 atoms of different electronegativity connected to each other? For example, consider this carbon-oxygen bond. Oxygen is more electronegative, so the 2 electrons that are shared between carbon and oxygen, the 2 electrons that form the bond between them, are pulled more strongly by the oxygen atom. This creates a difference in the electron density on the 2 atoms. The oxygen here becomes electron-rich, and the carbon here becomes electron-poor. This is usually shown with the symbol as seen here. You can also see it with this drawing here that represents the distribution of electron density, and you can see electrons are pulled more strongly by oxygen. This pulling of electron density is called induction. Now back to our example. We know that chlorine is more electronegative than carbon because chlorine is situated on the right side of the periodic table here compared to carbon. And for this reason, the electrons shared between the carbon here and the 3 chlorine will be pulled more strongly by chlorine atoms. This will create a difference in the electron density on the 2 atoms, making the carbon atom here an electron-poor atom. The carbon here will then withdraw electron density from the region that has a negative charge. And in this case here, it will be this region here. So there is an inductive effect withdrawing the negative charge from this oxygen here toward the carbon. And this effect will stabilize the negative charge. For this reason, this compound here, and due to the inductive effect, is more stable than this one. It is good to know that inductive effects reduce rapidly with distance. Take the following examples. In the first compound here, the group of chlorine atom is connected to the second carbon if we start counting from here. In this one here, they are connected to the third carbon atom if we start counting from here. Since the distance between this carbon here and the negative charge region is higher than this one here, then the inductive effects of chlorine here will be reduced. And for this reason, this compound here is more stable. Now let's do some exercises. For each of the following acids, let's draw the corresponding conjugate bases, then determine which one is more acidic. For the first compound here, let's start by removing the 2 protons. We will get the 2 following conjugate bases. So we can see that there is no resonance effect in both cases here, and that the negative charge in both cases is assigned to an oxygen atom. So clearly here, these two factors cannot be used to assess which conjugate base is more stable. How about induction? We can see that we have 3 chlorine atoms connected in each case to a carbon atom. To assess which inductive effect is stronger, we need to see the distances between this chlorine group and the region that has the negative charge. In this case here, if we start counting from here, we can see that the chlorine atoms are connected to the 4th carbon. In this example here, they are connected to the 2nd carbon. So the distance in here is less than the distance in this compound here. For this reason, the inductive effects here are reduced. So this compound here is more stable, the base is more stable, and therefore the acid is stronger. For the following example, we begin by removing the protons to determine the conjugate bases. In both cases here, we cannot use the two factors, resonance and electronegativity, to assess the stability of the bases. And the interesting facts here to notice regarding induction is that it is involving two different electronegative atoms, chlorine and bromine. If you recall from the periodic table, chlorine and bromine are situated in the same column. Electronegativity increases when we go from down to up. Therefore, this means that the chlorine is more electronegative than bromine. So, the pooling effect of electrons is more important by chlorine than by bromine. Therefore, the inductive effects for this compound here are reduced compared to this one. So this one is more stable. And since the conjugate base here is more stable, then the corresponding acid is more acidic. For the last example here, we do the same thing. We remove the protons to get the conjugate bases. Once again, resonance and electronegativity cannot be used to determine which base is more stable, but we see that chlorine was replaced by fluorine. So we need to compare these two electronegative atoms in order to determine which one has the strongest inductive effect. If you recall from the periodic table, fluorine and bromine are situated in the same column. And since the electronegativity increases in this sense here, then fluorine will be more electronegative than bromine. And so the inductive effects here will be more important. And for this reason, this conjugate base here will be more stabilized. And so the corresponding acid will be stronger.